To calculate these distances, we need to know how the universe expanded during the light's journey. Note that if a galaxy is far enough away, its apparent velocity will be faster than the speed of light, and its light would never reach us. It would be beyond the physical visible horizon for the universe. It's not that it is moving through space that fast, it's just that more space is being created per second between us and them than light can traverse in 1 second. Plugging in the numbers, we find that all galaxies beyond 14 billion light-years could never be seen here. GNZ11 is now 32 billion light-years away, so the light that is leaving GNZ11 now will never reach us. After Hubble discovered the universe was expanding, it was assumed that it started off with a tremendous expansion rate, and because of the gravitational attraction of all the matter in the universe, the expansion would be slowing down. Two major efforts were started in the late 1990s to prove that the universe's expansion was decelerating. Both groups used distant Type 1a supernova as their standard candles. Supernovae provide a luminosity reading that enables us to determine their distance via the inverse square law. This distance is called the luminosity distance. Type 1a supernova also provide a redshift reading that gives us the distance via Hubble's law. Luminosity and redshift combined can tell us if the universe's expansion rate is constant, decelerating, or accelerating. Here's how it works. First, we measure the luminosity of a distant Type 1a supernova like SN 1994d and measure its redshift. Then we map the distance between us and the supernova over time. If the expansion rate is constant, the luminosity distance and the redshift distance will be the same. But if the expansion is slowing down, the expansion rate in the past would have been greater than what we see now, which means it would have taken a shorter time to expand from its size at light emission time to its present distance compared to a non-accelerating universe. This would result in a shorter light traveled time, shorter distance traveled, and a brighter observed supernova compared to a non-accelerating universe. By the same token, if the expansion is speeding up, the expansion rate in the past would have been smaller than what we see now, which means it would have taken a longer time to expand from its size at light emission time to its present distance compared to a non-accelerating universe. This would result in a longer light travel time, larger distance traveled, and a dimmer observed supernova compared to a non-accelerating universe. This is what both studies found. The universe is expanding, and the expansion is accelerating. In order to more precisely analyze our expanding universe, modern cosmologists place a grid over three-dimensional space. We treat the distance between two galaxies, r, as a constant. Then, we set the grid's scale factor, a, equal to 1 at the present time, and vary it to account for changes in distance over time instead of changing r. Now consider a cube enclosing a volume of space containing some number of galaxies. With our scale factor approach, the amount of matter inside the volume remains the same as the volume increases or decreases. But the matter density goes down when the scale factor increases, and it goes up when the scale factor decreases. We see that the matter density depends on the scale factor. Unlike matter that moves through space, photons are attached to the space they propagate through. So an expanding space will impact photons in a way that does not affect matter. Here's a cubic volume of space with a photon inside. The photon's wavelength, lambda, is equal to the length of the cube, a. Its energy is equal to Planck's constant times the speed of light divided by the wavelength. As the wavelength increases with an increase in the scale factor, the energy decreases, unlike matter where it remained constant. We see that the energy density also depends on the scale factor. In fact, we see that the scale factor, A, is the only variable. In other words, the history of the universe comes down to the history of the scale factor. And the history of the scale factor depends completely on the contents of the universe and how that content affects the space it exists in. When we observe light from distant galaxies, we are seeing the light from the stars in those galaxies, and that light has absorption lines. The same lines measured in a lab give us the wavelength of the light at the time it was emitted. A stretching of the wavelength creates a shift in the spectral lines to the red. For our nearby galaxies, light travels for a relatively short period of time, so the stretching due to space expansion is small. Our use of the Doppler effect that shifts spectral lines as the basis for determining radial velocities provides excellent measurements. But as the distance increases to hundreds of millions and billions of light years, space expansion becomes the dominant factor. In either case, we continue to measure redshift, z, as the difference between the wavelength emitted and the wavelength observed, divided by the wavelength emitted. In this hypothetical example, we have an object with a redshift equal to 6. Once a model for the change in the cosmic scale factor over time is specified, redshift gives us a great deal of information. For now, we'll assume a flat, matter-dominated universe. First, redshift gives us an object's receding velocity. With our model, we have the object moving away at 6 times the speed of light. Redshift also gives us the actual cosmic scale factor at the time the light was emitted. It gives us the age of the universe at the time the light was emitted. And it gives us the amount of time the light was traveling. Redshift gives us the distance to the object at the current time, and it gives us the distance to the object at the time the light was emitted. You can see why astronomers rely so heavily on redshift measurements. We now ask, what could be accelerating the expansion of the universe? In the How Small Is It video book chapter on the Higgs boson, we covered how so-called empty space is actually filled with matter and energy fields. We model the waves in these fields as quantum harmonic oscillators. And, given the Heisenberg uncertainty principle, the zero-point energy for any wave in the field must be greater than 0. We have seen that radiation and matter in the universe are diluted as space expands. But zero-point vacuum energy does not dilute. In fact, the total amount of vacuum energy increases as the volume of the universe increases. In a small universe, it would have little impact. But today, it is estimated to be around 70% of the energy density of the entire universe. This zero-point quantum vacuum energy is called dark energy, and it is enough to force the cosmos into its accelerating expansion. As we observe the space around us,